Welcome to this explainer of the 2026 arXiv survey by Theodore McKeever and Ahsan Nazir, where we're going to unravel the absolute ultimate whodunit of physical reality. Today, we're taking a deep dive into the very foundations of quantum mechanics. We're exploring exactly how our universe operates on the smallest possible scales and why it continues to completely baffle the greatest minds in science.
So let's just jump right in with the big one, a central question that has stumped physicists for a century. What does the universe actually look like when we aren't looking at it? I mean, we know the math of quantum mechanics works perfectly. We use it to build the lasers and the computers you're probably using right now. But when it comes to the literal fabric of reality, the very act of observing something seems to create a massive philosophical mystery. To get to the bottom of this, we first have to crack open the quantum rulebook and look at the basic rules of the universe. We need to understand the fundamental laws that govern how quantum states evolve and actually get measured. That means starting with the foundational postulates of the theory, and specifically, the concept of where all these quantum possibilities live before they're ever measured. It's called Hilbert space. Now, don't picture physical 3D space as we experience it. Think of it more like this massive, incredibly complex mathematical arena. It's a landscape of pure potential, where a particle can exist in multiple states, or even multiple places, all at the exact same time. Now, back in the early days of physics, the go-to explanation for this was the Copenhagen interpretation. The authors of our survey note that this takes an epistemic stance. Simply put, that's just a fancy way of saying the math of Hilbert space only represents our knowledge of a system, not the physical reality itself. It treats quantum mechanics as a super powerful statistical tool for calculating probabilities, completely shying away from claiming it's a concrete picture of the physical world. And that leads us directly to our central villain, the measurement problem. This concept completely shatters our everyday intuition. If particles are just floating around as a blurry cloud of mathematical possibilities in Hilbert space, how on earth do they suddenly snap into a single definite reality the exact moment we point a measuring device at them? Man, did this cause some drama. It sets the stage perfectly for Einstein versus quantum reality, truly the battle for the nature of the universe. Things escalated pretty fast. After Copenhagen became the standard in the 1920s, Albert Einstein famously pushed back hard in the 1930s with the EPR paradox. He literally refused to accept that the universe operates on mere probability, arguing that God doesn't play dice. This theoretical war just raged in the background for decades, until the 1960s, when John Bell finally formulated a mathematical theorem to put these arguments to a real physical test. The lines in the sand couldn't have been clearer. On one side, we have Einstein championing local realism. That's the belief that objects have definite properties whether we look at them or not, and that absolutely nothing can influence something else faster than the speed of light. On the other side, Copenhagen countered with epistemic probability, claiming that reality is fundamentally just a blur of statistics until the exact moment of measurement forces a result. So how do you settle a debate like that? Well, Einstein thought quantum mechanics was just incomplete. But eventually, physicists found ingenious ways of testing reality with Bell's theorem, ultimately proving spooky action at a distance. This brings us to a frankly shocking breakthrough in our investigation. The universe actually allows for instant connections across vast distances. We call this nonlocality. It means measuring a particle on one side of the galaxy can instantaneously dictate the state of a deeply linked particle on the complete opposite side. That entirely defies the speed of light limits of classical physics. It is the exact spooky action Einstein was so afraid of. Physicists use some brilliant theoretical tools as investigative probes to figure this out. First, Bell's theorem proved that there are no hidden, localized classical rules that could possibly explain this quantum behavior. Later on, Hardy's paradox came along and provided even more logical proof against local realism. Ultimately, these tests proved beyond a doubt that Einstein's hope for a totally predictable, localized universe was mathematically impossible. The quantum world is fundamentally non-classical. Since Copenhagen leaves us with a bunch of unanswered questions and Einstein's local realism is out the window, physicists have proposed alternative quantum realities as other ways to solve the mystery. When you start comparing how different modern theories try to solve this case, a massive divide emerges. While Copenhagen relies purely on statistics and completely abandons both determinism and locality, alternative frameworks offer radically different mechanical explanations. Models like the Broglie-Bohm theory and objective collapse models completely rethink how the microscopic world functions to try and give us a more concrete reality.
Take the de Broglie-Bohm theory, for example. It actually gives us a fully deterministic universe, where particles have definite physical positions at all times. It's exactly what Einstein wanted. But here's the catch. It is explicitly non-local. It relies on this hidden, underlying pilot wave that guides these particles and instantaneously links the entire universe together. You get your concrete reality, but you have to accept instant universal connection.
Then you have objective collapse models. Instead of relying on invisible pilot waves, these models actually tweak the fundamental rules themselves. They introduce new physical dynamics directly into the standard equations. Over time, these dynamics force a quantum system to just snap out of its probability cloud and pick a definite outcome naturally. Theoretically, this solves the whole measurement problem without needing a conscious observer or a measuring device to trigger it.
Oh, and we definitely can't forget about contextuality, which is another major piece of the puzzle highlighted by the authors. In the quantum world, reality isn't just passively waiting to be uncovered. The very act of asking the universe a question fundamentally changes the answer you get. Think of it like a conversation. The specific properties a particle displays depend entirely on the specific arrangement of the measurement being performed. It's like how asking someone a question in a completely different context yields a totally different response. So, how does all this microscopic weirdness create the world we actually live in? Let's bring all this together and look at from quantum to classical. How does our everyday world emerge? This right here is the ultimate goal of McKeever and Nazir's survey. They want to explain how a universe built on bizarre probabilities, measurement problems, and explicit nonlocality somehow looks incredibly normal to our naked eyes. Understanding this emergence of classicality is all about figuring out how these weird quantum foundations scale up to construct the predictable, stable physics of things like baseballs and planets. As the authors note, by tracing the theory from its foundational postulates all the way to contemporary discussions of measurement, we realize something wild. We have built an unbelievably advanced technological society entirely on the mathematics of Hilbert space. Yet the true, underlying nature of the reality those mathematics describe remains one of the most fiercely debated topics in modern science. I want to leave you with this provocative thought to ponder the next time you look up at the night sky. With everything we've uncovered today about probabilities, non-locality, and the sheer power of observation, if the universe is really just a web of quantum potential waiting to be measured, what exactly is the cosmos doing when our eyes are closed? Thank you for exploring this mind-bending topic with me. Keep asking questions and keep exploring.